Hi and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about different coordinate systems, um, basically different bases that you could express vectors in. We're going to, in this course, this algebra-based course, predominantly be focused on 2D vectors, although time permitting, I will talk a little bit about three-dimensional coordinate systems as well. So what are the different coordinate systems that we might use? Well, in 2 dimensions, there's basically 2 coordinate systems. So 2D, we have 2 coordinate systems. In 3D, there's 3 commonly used coordinate systems, although other coordinate systems could be chosen. And of course, we're not considering as different coordinate systems rotations of one or both axes. We are assuming what might be called normal coordinate systems, meaning all of the axes are perpendicular, all the directions are perpendicular to each other. So basically in 2D we have there's 2 options. There's Cartesian. So Cartesian, named after René Descartes, by the way, so the C is capitalized because it's actually the guy's name. Cartesian, sometimes also called rectangular coordinates. And we have polar, or sometimes called circular coordinates. And that's it. Those are the 2 main coordinate systems that we would use, certainly the 2 that we'd use in physics in 2D. In 3 dimensions, we have 3 commonly used coordinate systems. Again, Cartesian. There's also kind of 2 versions of what might be called polar. There's cylindrical, which is essentially a blend between the Cartesian and the polar. And then there's spherical. And how do each of these work? In Cartesian, you're given an x and a y. In polar, you're given an r and a theta. In 3D, Cartesian becomes x, y, z. Cylindrical basically becomes r of some sort. Some people use an s or a rho here. But rho, theta, z. And then in spherical, you have an r, a comma, a theta, and a phi. Now, if we want to be consistent in our notation, I'm actually going to use an r here for cylindrical, and I'm going to use a rho here for spherical, even though that's reverse of what most people do. And the reason why I'm doing that is because if I've chosen this set of variables the way that I've chosen them, then things are defined consistently. So for example, in 2D, I might have an object that's moving around on the ground, and so x might represent the east-west direction or the left-right direction, and y might represent the north-south or maybe the forward-reverse direction. And so, maybe you're standing somewhere and you're given directions that say, like, walk 300 paces to the north, then walk 200 paces to the east. Well, that would be 200 or plus 200 for x, and 300 or plus 300 for the y. Okay. In Cartesian, you might be told go 300 paces north, then go 200 paces to the east, then look for something that is, say, 6 feet above the ground. All right, so a little above eye level. Well, that is Cartesian coordinates in 3D. We have the same plus 200 for x, the same plus 300 for y, and we've just simply added a 6 feet and an elevation, how high up do we need to go, plus 6 for z. Now, polar coordinates, going back to 2D, are basically equivalent to giving a distance and a direction. So in 2 dimensions, we might be told go 350 paces or go 500 paces or whatever. Let's say go 500 paces. But the direction, rather than being go north then go east, would be specified along the lines of go 500 paces in the direction of, let's say, 35 degrees east of north. Okay. And in polar coordinates, if you go to 3 dimensions, you kind of have 2 options for how to do that. One is to take literally that 500 comma 35 degrees east of north and retain that as a direction and then be told what elevation, so 6 feet above the ground. And notice that z has the same definition as Cartesian. They're both the same 6 feet above the ground. Notice that r and theta in cylindrical have the same meaning as in polar, r and theta. Okay, so what spherical coordinates look like then? Well, spherical coordinates basically means equivalent to saying start where you are and go 501 feet in a direction that is 35 degrees east of north, but also at an angle of elevation of, let's say, 1 degree. Okay, that would be your equivalent to spherical. So you're given an exact direction. I point this way, go along the direction that my finger is pointing, and go in that direction along a straight line for 501 feet. That's spherical coordinates for you. Now, I could kind of end there, but I actually wanted to give a sort of example by way of drawing for the 2 that are in 2D. Again, we're not really going to do much 3D coordinates in Physics 2, so I'm really focusing on these 2 for what's left. But imagine that I have a grid. For example, maybe this is the ground, and this is east, west, north, and south. Okay, imagine that you started here. So this is initial position. And imagine that you want to go to this location right here. So here's start, here's end. Now, how might you give directions for that? Well, either way, you're basically going to follow this vector right here, which my program has just redrawn as a nice straight line for me, but unfortunately is no longer hitting the end. So let's move the end to wherever my program has decided the vector will be. If I were to measure this angle right here, this angle would represent theta. And the distance along this vector would represent r. So this would be r comma theta. And so basically I just take out a compass, measure an angle. Maybe the angle happens to be I said 35 degrees east of north. This one looks more like 35 degrees north of east, or if you prefer, 55 degrees east of north. But the angle theta is taken, so theta is generally assumed to be measured counterclockwise, CCW, counterclockwise from whatever is our positive x-axis. And maybe I should leave a little space here so it doesn't bleed into itself, but plus x-axis or direction. Okay, so that's theta. R, this just is the total distance traveled. Cartesian, I would have to take basically this right here to be my x, and this right here to be my y. Now I'm not going to finish this little Pythagorean triangle other than to note that this is a right angle. That's for a different day. But this basically gives you a visual representation of your Cartesian and polar coordinates. Now note that in Cartesian, this would be plus x, comma, plus y. If I were to write it in polar instead, by convention, I usually use a curly bracket when I'm writing out polar coordinates. And r is always taken to be positive, theta generally taken to be positive. But we could say like plus r and plus theta here. Now if I wanted to go into a different coordinate quadrant, maybe we could draw out the different possible quadrants. So there's one here, there's one here, there's one here, there's one here. We'll call this the y-deck and this the x-axis. This one right here would be plus x, comma, plus y, and plus r, comma, plus theta, where we could write that 0 is less than or equal to theta is less than or equal to 90 degrees. This one right here we'd say is negative x, comma, positive y, and we could also say plus r, comma, plus theta, where 90 degrees is now less than or equal to theta is less than or equal to 180 degrees. So notice that the only thing that's really changed for the polar is just the bounds on theta. This quadrant, the third quadrant, is my negative x, negative y quadrant. And again, we could write plus r, comma, plus theta. We could take a minus theta, in which case we're going clockwise from the x-axis. But if we use plus and plus, then we have 180 degrees less than theta less than 270 degrees. And this quadrant right here would represent plus x, comma, minus y. And again, we could do plus r, comma, plus theta, where again, theta has a value between 270 degrees and 360 degrees. Okay, and that's it. That's our coordinate systems for 2 dimensions, kind of visually represented. We might maybe like draw out the vector. So here are some vectors to represent each of those. But other than that, we've got polar and we've got Cartesian coordinates. I'm not going to try to draw the 3D coordinates for obvious reasons of my lack of artistic ability. Some textbooks do have those shown though. So, thanks for watching.